In this slide, we will look into post-optimal analysis of linear optimization problem. First of all, let's look into why do we need to do post-optimal analysis. Let's take an example of a factory which produces certain number of products using certain number of raw materials. Okay, as we know, due to seasonality or due to various other factors, there may be change in the demand of the products or there may be change in the supply of raw materials. Thus, while designing a problem for maximum profit of a company, we need to change the parameters in the design problem every time when these changes happen. So instead of this, we can use the existing solution to find the new solution by following certain methods mentioned in post-optimal analysis. There may be change in the supply of raw materials and thus this would reflect into the change in the right hand side of the constraint. There would be addition of a new raw material and thus this would lead to addition of a new constraint. This both would affect the feasibility of the existing solution. There may also be change in the price of the products or there may be addition of a new product. And thus this both would affect the optimality of the existing solution. Thus there are various conditions which are there after there are parameters changes. For example, if a current solution remains optimal and feasible after parameters change, no further actions is necessary. If a current solution becomes infeasible, we need to use dual simplex to recover the feasibility. If a current solution becomes non-optimal, we need to use primal simplex to recover optimality. If a current solution becomes both non-optimal and infeasible, we need to use generalized simplex method to obtain the new solution. For studying various parameter changes, we would look into a problem, Toyo problem, in which x1, x2, and x3 are our design variables. We need to maximize this objective function, which is subject to three operation conditions. We found the optimal solution, which is x1 is 0, x2 is 100, x3 is 230, and the optimum solution is $1350. We also found the solution for the dual problem. Now, this is the optimal table of the primal problem which we had seen earlier. So, as we looked earlier, there may be two uh, possibilities which would affect the feasibility of the existing solution. One is the change in the right hand side, and the second is the addition of a new constraint. We will look into changes in the right hand side of the constraint firstly. So, to find the new solution from existing solution, when there is a change in the right hand side of the constraint, we follow this method in which there is a formula which is inverse in iteration I into new right hand side of constraint. Through this in matrix multiplication, we can find the new right hand side of the table, which is nothing but the solution of the problem. In this slide, we took an example in which the constraints right hand side changed to 602, 644, and 588. Through matrix multiplication, we got the new optimum solution, which is x2 equals to 140, x3 equals to 322, and x1 is 0. And thus, the optimum revenue is $1,880. As we see, we did not design the whole problem again. We found the new solution using the existing solution by following a simple method, which is nothing but a formula which is shown in the slide. There may also be addition of a new constraint, as we have seen earlier, which is, let's take an example of addition of operation 4 in the problem, which is 3x1 plus 3x2 plus x3 is less than 500. Okay, we see that when we introduce the slack variable x7 of this equation in the tabulae, we see that the x2, x1, x2 and x3 values are not consistent with the x7 value. Thus, there may be two conditions which would happen after addition of a new constraint in the tabulae. The new constraint is reducting, meaning that it is satisfied by the current optimum solution and hence can be dropped from model altogether. Or the current solution violates the new constraint, in which case the dual simplex method is used to restore feasibility. In our problem, the x7 equals to 500 is not consistent with the values of x2 and x3 in the rest of the table. Thus, we need to uh, solve the problem using dual simplex. The basic variable x2 and x3 have not been substituted out in the new construct, which will be substituted by new x7 row. And thus, the new tabula would be this one, which is shown in this slide. By application of dual simplex method will produce the new optimum solution. And thus, by solving dual simplex solving this problem using dual simplex, we will find the new solution as x1 equals to 0, x2 equals to 90, x3 equals to 230, and z equals to 1370. And thus, again, we see that we have found the new solution using the existing solution without redesigning the problem again. And thus, that's the benefit of post-optimal analysis. Thank you.